Okay. All right, we're going to talk about the three discoveries. So let's see what they are. Let's look at the next click and see what we got. Okay, the first discovery is that dark rays make light and material. That's due to Einstein in 1905. Let's look at the second discovery. Second discovery is that the universe is expanding. And the third discovery, the first light that's shown in the universe is the most perfect light that science has ever analyzed. That's attributed to Penzias and Wilson in 1964. Now, believers, suppose God let you see something as it came in its pristine state from his hand before the universe had any sin in it. What would you expect? Okay, let's go on to look at these discoveries in more detail. First one, Albert Einstein made the first discovery in 1905 when he was 26 years old. He produced the famous formula E equals mc squared. Einstein's theory is called relativity. A consequence of relativity is that very energetic rays can make subatomic particles, the bits and pieces one needs to put atoms together. Let's understand what kind of rays can make particles. It will not do to shine two strong flashlights at each other, however intense the light may be. We will not find particles falling out when the two beams of where the two beams cross. That's because light rays, light that we can see, are not energetic enough to make particles. Ultraviolet rays are not energetic enough either. However, there are two kinds of rays that are still more energetic. If we make them, we call them X-rays. If nature provides them, they are gamma rays. The most energetic X-rays we can make are as energetic as some of the less energetic gamma rays. Now, you can't see X-rays because they are dark. That means not visible to our eyes. But you know that X-rays exist because when you go to a medical lab for a X-ray or a radiograph, the X-rays produce a photograph of your insides. So something went through your body and exposed the film. You didn't see anything, but something happened. Let's go on. Now, in this picture, I have drawn two gamma rays as wiggly lines. You see, they have a little letter gamma, and there's two wiggly lines, and they collide in the interaction region. I've shown the interaction region as a kind of dust cloud because we don't know exactly what goes on, but if you've ever seen a cartoon of Calvin and Hobbes fighting, with a fist coming out of the dust here and a tail coming out of there, you know what I mean. Let's try the next step here. Next click. So there's the two gamma rays colliding in the interaction region. Then next, the two rays may collide and materialize as two particles. This means that the rays disappear, and instead, out of the interaction region, I've drawn two particles. One of them I've called E minus. In this case, it is an electron, and E plus is the same as E minus, except that the charge is positive rather than negative. So that is sometimes called a positron, or a positive electron. Now, we call this collision materialization because the electron and the positron appear where no material was present. The vacuum was not truly empty, however, because it had the two gamma rays in it, and it was their energy that disappeared to produce the two particles. Okay, let's see if there's one more click on this. So there they appear. Okay, now the reaction is reversible. If a positron meets an electron, they will annihilate each other. That means that the particles disappear, and in their place, there are gamma rays leaving the region. Whether there are 2 or 3 gamma rays depends on how the particles are spinning when they come together. Now, there's many reactions like this. Experiments of this nature go on daily in physics labs around the world, wherever there are cyclotrons or linear accelerators. Let's go to the next slide. In this, an X-ray hits a molecule. Now let me see, what did I do with the mouse? Is right here. It had a laser, I guess. Oh, okay. We'll see if the laser pointer will work, even if the radio doesn't work. Okay. Oh, okay. Oh, okay. Now, you'll notice a little letter S that stands for the source. The X-ray is invisible, so it is proceeding down from the source, and it hits a molecule at the letter M. And then, at that point, something happens. The X-ray bumps into the molecule, and it chips out an electron. There's an E minus, and the E minus spirals around counterclockwise, but also a positron appears, and it spirals the other way. This is a picture of an actual experiment. The reason why they spiral is because there is a magnetic field you can't see that is perpendicular to the screen, and the two charged particles move in opposite directions in the magnetic field because they have opposite signs. So later on, the molecule, the rest of the molecule that lost its electron is much more massive, so it goes on in a curve down toward the right. It would make a huge spiral way off the screen. It is positively charged because it lost an electron. Therefore, the net charge is positive, and so it makes the same kind of circle that the positron makes, but a much wider one because it is much more massive. Then the X-ray further comes down to the point A, and it bumps into another molecule, and it also knocks particles off that, breaks it up, but it doesn't have enough energy left to make a positron because most of the energy of the X-ray has been used up. Okay, let's unpack this question about the. Okay, yeah, right here is the path of the X-ray. Now let's see, go like this, and we. Okay, can we advance it another to the next slide? That's right. Okay, that's here. So those are the three things I just talked about. Let's go on to the next slide. Okay, E equal mc squared. Let's just talk about this formula. If you leave out the c squared, it's easier. The energy E is equal to the mass m of particles. So energy is equal to mass of material. Now, we have to multiply by c 2 times because we measure energy and mass in different units. Let's look at the next click on this. There is c. C is the speed of light in a very large number, an exact number of meters per second. A meter is a little bit more than a yard, so it covers in 1 second a very great distance. It could go around the world 7 times in a second. Then another click. Suppose that the mass is 1 kilogram. That would be just a little over 2 pounds. Then we would get E on the next click. And E is, you see, we have to multiply by c squared. That's a very big number. We're multiplying c squared times 1. So we're getting something like, if I can read this correctly, thousands, millions, billions, trillions, 89 quadrillions of watt seconds of energy. A watt second is the amount of energy it takes to keep a 1 watt light bulb burning for 1 second. You can get it down into units that are easier. Let's click again and see. Okay, that would be 25,000 million or 25 billion kilowatt hours of energy. And how much would it cost at current rates? Let's look at that. $2.4 billion. So you see that a little bit of material goes a long way to making energy. Conversely, it takes a lot of energy to make a little bit of material. Okay, now, this illustration makes us realize that to make an entire universe from energy would require an extremely powerful agency to do the work necessary to produce the energy. And if the universe turns out to be infinite, then the agent would have to be omnipotent. You may have heard of agencies like that. Actually, that would be an agent. Let's go to the next slide. Now, 10 years later, in 1915, Einstein generalized relativity to include the effects of gravity. Let's see what we have in there. Okay, and then another click. And another. Okay, now gravity, you may have noticed, only pulls, it does not push. But Einstein saw that this makes the universe unstable. Let's take another click at that. Because if the universe is all spread out and the stars and the galaxies are all out there, they're all pulling on each other, but there isn't any lattice work or skyhook or poles that keep them apart. So therefore, if they're just pulling on each other, pretty soon they're going to fall in on each other. And Einstein didn't like that. We wouldn't like it if it fell in and the life were crushed out of us, but we're not crushed, and we can see galaxies in the sky. So Einstein foresaw that the galaxies might be moving away from each other. But in that case, the universe could not be eternal and changeless either. Now, because if they were all moving away, then after a whole eternity of moving away, they would be infinitely far away, and we couldn't see any of the galaxies because all of them would be too far away except our own galaxy. So the fact that we can see galaxies a large but limited distance away from us shows that the universe began at a large but limited time ago. Now, Einstein preferred an eternal, uncreated universe because he recognized that if there was a beginning, then he would have to admit that there was a creator. And for Einstein, this was too similar to what the Bible says in the book of Genesis. Einstein had already decided as a teenager that many of the stories in the Bible could not be true. Nevertheless, the equations that Einstein had just written when he generalized relativity pointed to a picture that was uncomfortably similar to what the Bible says. So what did he do? He looked over his equations and he saw he could add a constant. Let's see this. Got that. He added what is called the cosmological constant, and he chose a value for it that would nullify the effect of gravity at long distances. So we could have nice local gravity on Earth to help us stay put on the planet and keep the air around us and the water and all our things from floating off. But at long distances, it would not unstabilize the universe. So presto, with a little constant added, and choosing the right value, he could have an eternal, uncreated universe that was not unstable, that was stable. It could last that way forever. Now, the constant was so small that its presence or absence could not be verified by experiment in any earthbound laboratory. Remember, it only was effective at very long distances. So, confident that no one could disprove the existence of the cosmological constant, Einstein was pleased to see that his equations did not now require a creation for the universe. Okay, this leads on then to a second discovery. That was in 1915. Along comes, let's look at the next slide. Let's look at Edwin Hubble. Edwin Hubble was an astronomer. He liked to go fishing on his day off, and astronomers have all their days off because astronomers do their observing at night. But 14 years later, Edwin Powell Hubble, using the largest telescope available in his day, discovered that the universe is indeed expanding. So Einstein only had 14 years of feeling good, and then along came Hubble. Now let's look exactly at what it means for it to be expanding in the next slide. Here is, on the left, a picture of the universe, and it has several galaxies sprinkled around it. Now, the expansion doesn't mean that everything expands. The solar system is not expanding. The distance between the Earth and Sun is not expanding. If it were, we would soon be freezing in the dark. And the galaxy is not expanding because it has gravity that holds it together, and it has spin that keeps it from falling in on itself, and it has some other things that keep it nice and stable. But if the space between the galaxies, you see in the other two pictures, now the space is doubled, and in the third picture it's tripled. The number of galaxies is the same, but the spaces between them have increased, but the number has not increased. Let's go over this point again in the next slide. You see, in the left side we have revolution. We have the sun in the middle, the Earth, and there's a red vector arrow pointing toward the sun because the sun is pulling on the Earth. But the Earth is also moving in its orbit. The line that is perpendicular is parallel to its position in the orbit, and as it moves around, it has motion that is perpendicular to the force of gravity. Now that motion produces inertia. An object will continue with its same state of motion unless some force is acting on it. But that motion produces a fictitious force, it's shown by the green arrow, that exactly compensates for the gravity, so that the Earth keeps on going around the sun. Every year it goes around another time, and it doesn't get far away, so we don't freeze in the dark, and it doesn't fall into the sun, so we don't get burned up. Now, if you take a look at the diagram on the right side, there are two galaxies, and all they're doing is pulling. So even though they may be expanding, they're pulling. The problem is that expansion is not stable. Let's see why that is true. If you throw a ball into the air, the distance between the Earth and the ball is expanding. But as the ball rises, it keeps on slowing down till for a moment it comes to a stop at the top of its movement, and then the movement reverses and it starts falling down again, so that the distance between the ball and the Earth is now contracting. All right, well, the thing is that Einstein could add expansion, but it couldn't go on forever and make an eternal universe. So let's look at the next slide. Einstein had foreseen and rejected the expansion in 1915. He then, in the next click, Hubble's discovery upset and angered Einstein. Now, why should he get angry? It's just a fact of nature, you know. But in any case, in the next click, after a while, Einstein cooled off. He went to Mount Wilson in California. You can see him there looking through the eyepiece of the telescope, which I could see the dome of it from the backyard where we lived in California. He looked through the eyepiece of that telescope. Hubble is behind him, looking a bit worried. But Einstein accepted the expansion of the universe and apologized. At that point, he needed to apologize to Hubble. Then in the next slide, Einstein confessed to his friend George Gamow, who is shown over there on the right. He confessed to George Gamow that adding the cosmological constant with the value he chose to his equations in 1915 was the biggest blunder of his scientific career. If he had not been so busy trying to make an uncreated universe, he could have predicted Hubble's result, because that's what the equations were telling him. So why did he make a blunder? There was nothing wrong with Einstein's math nor his science. It was his rebellion against the Bible and his preference for an uncreated universe that led him to add the cosmological constant and to choose its value without any scientific reason. Okay, now George Gamow was a physicist who was very interested in atomic explosions, and he suggested that if the universe had a beginning, it may have been like an atomic bomb or like an explosion. The flash of the atomic bomb lasts a fraction of a second, but years later one may still detect radiation left over from the explosion. So Gamow suggested that we might detect some residual radiation left over from the beginning of the universe. A physicist named Robert Dicke at Princeton began looking for that radiation from the beginning of the universe. So let's look at the next slide. Now, unknown to Robert Dicke, there were two scientists at Bell Labs, Arno Penzias, shown on the left, and Robert Wilson. And in 1964, they were not looking to detect radiation in the cosmos or anything like that. They were working on making microwave systems for transmitting telephone over long distances. Microwave towers are used for that. But they had a very big microwave antenna, which was movable. If you can see behind the elbow of Wilson, you can see the door to the control cabin. And the orange part is the large horn that could be pointed in various directions with the gimbals and so forth, so that they could look anywhere and see if they could detect interference that might bother microwave communications. And when they did that, they made a discovery which earned them a Nobel Prize in 1978. Okay. Let's look at the next slide to see how this worked. Now, I've shown the antenna in 3 different positions. And in the left, when it is looking around the ground, along the ground, they discovered that they picked up a lot of noise that would interfere with could interfere with microwave communications. We've called that level 100%. When they raised the antenna, as in the middle, so that it was looking at the sky, the noise that they got dropped to only 30%. So that means that 70% of the noise was human-made noise from electric motors, equipment in hospitals, things like that. But there was some that was coming from the sky. Well, that could be from our own sun and other stars that emit radio waves. But if they searched around in the sky, as in the right, and pointed the telescope at, or the antenna at a piece of sky that had no stars or very few stars in it, they could get the noise level down to 1%, but they could not get it lower than that. And the thing is that this 1% seemed to be coming from beyond the stars. See, because if the stars were not in the background, it was still coming in. So if the waves come from beyond the stars, then they come from before the stars, before there were stars. And so the wave would come in. So let's look at what kind of antennas were used to discover this in the next slide. NASA has 3 huge antennas. 2 of them are in California and Australia. I visited the one in California. The discovery was so important that NASA studied it with its deep space tracking network. In the next slide, you'll find where the 3rd antenna is. It's in Spain, near Madrid. Okay. Now, let's go to the next slide and address the question. How is it possible that we can still see the first light? Because if it started a very, very long time ago at the nearly the beginning of the universe, then that's been a long time ago. So how can we possibly see it? All right, I have shown there a region, and if I can figure out where I put the, right, okay. I've shown here the region, a little spot where the Earth would later be formed. And according to the Bible, God noticed it was all dark, so he said, let there be light. So that region started to burst with light. And then if you count the number of years since creation, the light could get to there. Actually, it could get to the sphere or a circle or a sphere centered around the Earth. Okay, that light we can never catch up with that light. We can never see the light that came from the region where the Earth would later form, because if we wanted to do that, we'd have to jump in a rocket ship, get off from the Earth, and get away around here, then turn back and take a look. But we'd have to be traveling faster than the speed of light, and that's illegal. According to Einstein's theory, you can't go faster than the speed of light. However, when God said, let there be light, in 2 Corinthians 4:6, he didn't just say, let there be light. He said, let light shine out of darkness. Now, when he said that, all the darkness responded at once. What darkness could or would resist God's command? So it all shone at once. Therefore, everywhere, light was bursting out. Now, I have shown just 4 regions similar to the one in the center, but actually everywhere light was bursting out. And therefore, the light that was bursting out of this region, for example, is some of it was pointed toward the earth. And since it's had the same number of years since creation, that light is just now arriving at the earth. And the light is coming from every direction. So we can still see the light that shone when God said, let there be light. Now, it's coming all the time. You can't see it because it's too weak for our eyes. But with the proper detectors, you can detect it with instruments. All right, let's look at the next slide. Let's see, just to review, some of the first light went out. Now the light's too far away to see. And from the distant circle, another part is now arriving. Let's go on to the next slide to look at the sun's imperfect light. Because remember, we said that the first light was nearly perfect. Okay, in this picture, we have three different views. There you can see this red part. This is the light that one would see at sunset when it is just grazing the earth. And you can see that it is not a smooth curve at all. It's got big places where H2O, that is water, and other things absorb the light. There's CO2, so carbon dioxide also absorbs the light. There is O3, that's oxygen, ozone, I should say, that also absorbs the light when it's coming through the atmosphere. Now, if we get above the atmosphere and we look at the sun, and that's the sun with its yellow light, you can see that the curve is also not quite smooth. It's got some jagged lines, and those are basically because the atmosphere of the sun has things like iron vapor in it. Iron is so hot it's not just melted, it's vaporized. And therefore, it is not smooth. But a smooth curve is this black curve marked by Max Planck in 1900. This was the first law ever discovered of quantum mechanics. And let's see, we are going to see in a minute how the light came in. Let's look at the next slide. Here is the same, the solid line is the same curve, the Max Planck's curve. The squares are the error when the first observations of the light that was coming in were measured just 7 weeks after a satellite first went up to measure it. And what you will notice is that the little boxes correspond exactly all the way. There's no deviation. After several years of taking data, the difference between the theoretical curve and the first light of the universe was on the order of a part in 50,000. It was that perfect. Now, God only said it was good. He didn't say it was perfect. But he was being modest, as one should be when talking about one's own work, I suppose, but and modeling for us. But anyway, it is the most perfect light science has ever analyzed. but the imperfections also are what made it possible for the universe to support life. Now, I want to show you a map of a color map of the first light. But first, I want you to look at this map. This is a picture of the Earth. It doesn't look like that from space because you can only see one side when you're in space. But we have a way of putting it into an oval so you can see both sides. This is a picture of a color temperature map of the Earth on a day in June, in which, therefore, in the northern hemisphere, it's summer, and you can see that the hottest regions, the reddish regions, like the Sahara Desert, and in Mexico, and in India and Arabia, are all north of the equator, which is down here. And then the coldest regions are in the southern hemisphere where they're having winter. When we have summer, they have winter. And the coldest region is down here in Antarctica. Now, so this just gives you an idea of how to make a map showing in which color shows temperature. So now let's look at a map of the first light on the next slide. When they received their data, the first picture that they got looked just like this. The red shows the warmer region and the blue shows the cooler regions. All right, this variation over the whole galaxy, over the whole universe, actually, is very systematic. It just means that the Earth is moving with respect to the background light. So they can compensate for that by just subtracting this effect off. So in the next slide, they got a picture like this. Now the coordinates are centered on the Milky Way. And what they got was this mottled, blurry picture of the first light with, for instance, large cool regions here and large warm regions up there near the poles. But they had this great band across the middle of it. Well, that's just our own galaxy. We can't observe outside our galaxy. And so the galaxy, of course, has bright stars that produce interference. So the people spent about a year subtracting off the contribution from the known positions of stars in our galaxy, and they got the next picture. And in this picture, the distribution is random, but you can see that it is not quite uniform. Here is a large cool region, here is a large warm region. Now the thing is that the different regions are where fewer or more gamma rays collided and made material. If in a cool region, fewer of them collided, fewer of them formed material, and in the warmer regions, more of them collided, made more material, and there was also more leftover heat to make it warmer. All right, well, if there's more material, then there's more gravity. Therefore, the hot regions pulled harder than the cool regions. So therefore, they started stealing material from the cool regions, and it moved into the hot regions. This, the poor get poorer and the rich get richer. But that was what changed the aspect of the sky to what it looks like now. Let's go to the next slide. First, I just want to show that since then they have made another picture which is much more detailed. This picture shows the morning stars and singing together, but I can't go into that right now because our time is running out. So let's go on. And I wouldn't bring it up to the unbelievers anyway. Let's go to the next picture. Okay, now I've shown up above the aspect schematically of the universe where there were warmer regions and cooler regions. Let's look at the next click on this. The hottest and densest regions like these pull harder than the others. Then the next click, is they become compact, they heat up, and there they form galaxies and stars. And so in the next click, what happens is that they leave behind a space which is dark and cold. This is the aspect of the sky that you see now. You see points of light separated by a dark void. All right, well, why is that good? Let's go on to the next slide. To review, let's look at the first click here. What we just showed, by the way, is that the light separates from the darkness. It separates from the darkness because of its own gravity. That is, the light pulls itself together and leaves the darkness behind. Now, these discoveries, the three discoveries, are counterintuitive. The idea that energy can turn into matter, whoever heard of that before the 20th century? Or that galaxies are moving away, you can't see them because they move too slowly for us to see. And the idea that the first light is still detectable, that just doesn't seem right. Let's click this again. As a matter of fact, no ancient philosophers anticipated the discoveries. And another click, the discoveries needed cyclotrons, telescopes, and satellites for their confirmation. And that was not available until the 20th century. So therefore, we could not make a model they could not make a model in ancient times. Now, let's look just briefly at some ancient cosmologies. Here's, next slide shows one from India. This is the Earth on the backs of 4 elephants on top of a turtle. Could you click the slide again? Now, this is basically to answer the question, if everything falls, why doesn't the Earth fall? All right, if you click again, you'll see that Einstein asked, why doesn't the universe fall in on itself? Okay, so one cosmology said, well, the Earth is on the backs of these elephants, and they have to stand on something, so they're standing on a turtle. But you'll notice that underneath the turtle is a shadow. The turtle is standing on some sort of other Earth, which is not mentioned in this cosmology. Okay, let's look at the next slide. Why doesn't the Earth fall? That's the Earth as seen from space, and it hangs on nothing, as it says, he hangs the Earth on nothing in James. Let's click on that and see. Now, here's another cosmology that comes from the pyramids. In this, the sun appears 3 times. The sun has to rise in the darkness, and then it has to be at midday here, and it goes down in the evening. The Earth is this man named Shu, who has his suit covered with ears of grain and so forth, because that's the, and it turns out that his brother to, that was Geb the Earth, this is on the skies or the heavens, who doesn't get tired of making an arch of her body over the Earth, and they have been creating incest have produced a son, Shu, which is the air, the atmosphere. He floats on nothing, although he seems to have a little support down here. Now, so the sun rises every day in the east, then it goes over, and then it sets in the west and goes down into the place of the dead. But somehow, the next day, it makes a trip down underneath and comes back up again. So the question, that was a great mystery to the ancient people. How does the sun make this trip and come back again? Okay, so the problem with all this cosmology is that if you have so many gods in charge of everything, then there should have to be a super god that would create and organize them. Also, you'll notice that underneath the heavens and the earth, there is a platform. See, so they can't get away from something to support them either. All right, let's go on to one other ancient cosmology. This ancient cosmology, which is found in Genesis, and I've just shown the first about 8 verses. Let's look at the coincidences. The first click, it says, there was a beginning. In the beginning, God created the heavens and the earth. There was a beginning. Einstein wanted to avoid it, but there it is. Second, God saw that the light was good. The first light is as nearly perfect as it can be, but the irregularities enabled it to form stars and galaxies and planets and cool places for the heat to go so that we could have a place which not too hot, not too cold, Goldilocks just right, where we could live. Okay, the third coincidence is that the Bible says God separated the light from the darkness. And I just showed you that he accomplished that by letting it use gravity, which he had created. So, of course, God did it, but he did it according to the laws that he had created. And finally, the other discovery. In 4 places there, the Bible says God put an expanse. He put expansion in the heavens. The heavens are expanding. So, the question is that I've posed to unbelievers, how did Moses get it right? He did not have access to cyclotrons or telescopes or to satellites, but thousands of years before those instruments were known, he took the 3 major discoveries of cosmology of the 20th century and interwove them correctly into a coherent story. Okay, now I'm not going to ask you that question because believers don't have any problem with that. God knew what he had done, and he communicated it with his servant Moses, who wrote it down. I have never found anybody who could challenge this question or could answer apart from the belief that God created the universe and that he communicated it in his word. So at this point I would answer questions from the audience, but I've faced many hostile audiences with people trying to defeat me, and nobody has ever defeated this argument because I'm using their data against them, see? Let's go to the next slide. I just want to point out that I've made a booklet on the left, which I've distributed more than 1,000 copies. It's it includes my testimony, and it is ideal for giving to a unbelieving nephew or somebody. And even if that nephew has a PhD in physics, nobody has ever found any scientific flaw. So it would be a way of testifying that he would, dismiss it as trivial or something, or I have had people attack me, not my message, but me. That is strictly forbidden in science because personal attacks are ruled out because it doesn't matter who you are, the truth or falsity of what you say will be determined by the scientific evidence, not by your reputation or something like that. So in a way, I've had a vindication because when people attacked me, that showed that they were not being scientific and they didn't have any other way to refute me other than a personal attack. So the other is a DVD, and I made that in 1910 with 2010. I'd made that in 2010 with the same talk, but I was younger then, so you'll notice that. Okay, we've gone over the time, and I appreciate your indulgence. I'd be glad to answer your questions. And yes, Carolyn has some of the materials at the book table, or at the table in the entryway if you want to buy them, if you have anybody you want to give them to. So, you've been holding all your questions. Go ahead and let me have them. I must say that it's been years since anybody asked me a new question. Yes.
When you would do these presentations and people would ask you questions, what was maybe the most recurring things that people came back with, like challenges or whatever?
Right. I used to say that there were less than 50 questions that atheists asked, but one time I was doing a radio show, and there was somebody in the studio known to the host who was lying in wait for me, and he was throwing at me all these questions right and left. But I was thinking, oh boy, here we go again, shooting clay pigeons and just answering the questions. And in the end, I had answered all the questions, and the time had run out, but the host read my resume to humiliate my attacker. And of course, it had all gone out live, so they couldn't just take it back or, refuse to do it. Well, anyway, we got back to where I was staying. They had recorded the broadcast on the radio. So I sat down and I made a list of the questions. And I discovered something. There are not 50 questions. There's only 19. And I have good answers for all of them. So let's see, let me explain how it went one time at the University of Seville. We got a room that seated 120, but we had 30 standing in the back, completely filled up. Their biology department had gotten word that I was going to be speaking about creation instead of evolution. So the graduate students were out in force trying to trip me up. And in the question period, they spent a solid hour asking me every conceivable question that they thought would embarrass or be too difficult for me to answer and so forth. And I was just, shooting them down left and right because I'd heard all the questions. I even had slides ready to show them for the answers. And anyway, there was one Christian graduate student in the biology department, and he reported that the next day in the graduate student lounge for biology majors, he said there was absolute rage that they hadn't been able to trip me up. So that's what, if the Bible, if the Word of God is preached with power, it either convicts or enrages. And in any case, the people cannot say that they did not receive a witness. Okay, well, I think we should wind up here because I've already overstepped the time limit. But thank you very much for your attention.
your word is true, and that you draw us together to you. We're all different backgrounds and everything else. Lord, we thank you. Thank you for Jesus Christ. Tonight is thank you that we can stand here tonight and say that you are truly God. We sang you are holy. You are worthy of all our praise. And for this testimony tonight, to you and your sons, Lord, you stand true above all things. Thank you that you rule and reign today. You rule and reign in our hearts, and we ask that you would continue to draw us closer to you. Our hearts would even melt before you as we continue to come closer to you, that your word would fill our hearts, fill our lives, that your power would rule in us, and that we would really be witnesses as the heavens and the earth declare your glory, Lord. May you use us to also here walking on earth in the midst of your creation to also declare your glory. May you reign in your church.